Have you ever wondered why an AI might make a biased prediction? Like, what if a medical AI diagnosed brain disorders, but relied more on a patient's age than their actual symptoms? That's the problem of confounders, hidden variables that distort machine learning models. Today, we're diving into a breakthrough that helps AI learn fairly, even as data evolves over time. So what's a confounder? Think of it as a sneaky third factor. Imagine a study linking ice cream sales to drowning incidents. The real culprit isn't ice cream, it's summer. More people swim in hot weather, leading to more drownings. The summer variable is the confounder. In AI, confounders like age, gender, or even imaging equipment can trick models into making biased decisions. This is especially tricky in continual learning, when models learn from new data over time, like a doctor diagnosing patients year after year. Traditional methods try to remove confounders by adjusting features, but they struggle when data changes. Picture a model that forgets what it learned earlier when faced with new information. That's catastrophic forgetting, and it's a big deal. Enter Recursive MDN, R-MDN. This new technique acts like a smart filter in neural networks. Instead of relying on old data, it updates itself in real time using recursive least squares, a mathematical method that adjusts models incrementally. Think of it as a self-correcting system. Every time new data comes in, R-MDN refines its internal model to minimize the influence of confounders, like age or imaging protocols. Here's the magic. R-MDN works at any stage of a neural network, whether it's a simple model or something as complex as a vision transformer. It doesn't need to relearn everything from scratch. Instead, it continuously refines its understanding, ensuring predictions stay fair even as data evolves. In experiments, R-MDN outperformed older methods. It reduced biases in medical imaging, like skin cancer detection, and kept models accurate across different patient groups. Whether it's a cross-sectional study with one-time data or a long-term clinical trial, R-MDN adapts without forgetting. Why does this matter? Imagine an AI that doesn't just get smarter over time, but also becomes more equitable. From healthcare to self-driving cars, this could mean fewer biases and better decisions. The future of AI isn't just about learning, it's about learning the right way. So next time you hear about AI making a decision, remember, the tools we build today are shaping a fairer tomorrow. Thanks for watching, stay curious. Ever wonder why AI models sometimes forget what they've learned when tackling new tasks? Or why some systems struggle when data changes over time? Today, we're exploring a cool new approach called R-MDN that helps machines learn continually, like humans do, without losing their grip on old knowledge. Let's break it down. Traditional AI models rely on batch statistics, averages calculated from groups of data. But this can be a problem when data shifts, like a model trained on old photos having to learn from modern ones. Or when there's a confounder, a hidden factor that skews results, like a camera's lighting affecting image quality. Here's where recursive feature normalization comes in. Picture it as a self-correcting filter. As the AI processes new data, it constantly adjusts its focus, stripping away irrelevant patterns that could lead to unfair outcomes. It's like training a student to solve math problems without letting them copy answers from the teacher's habits. The magic here is continual learning, the ability to adapt over time without forgetting what it already knows. Traditional models struggle with this, especially when new data introduces fresh confounders. But recursive feature normalization uses a clever trick called recursive least squares to update the model incrementally. Think of it like fine-tuning a recipe as you go, ensuring each new ingredient data point doesn't throw off the whole dish. Let's get real-world. The researchers tested their approach on datasets like ADNI, brain scans for Alzheimer's, and HAM10000, skin lesions. They created synthetic data too, like digital playgrounds where they could control the rules. The key: they wanted the AI to focus on true clues, like tumor shape, while ignoring distractions like a blue marker in the corner. Here's where their method R-MDN shined. It achieved top accuracy while almost completely ignoring the confounders. Imagine a model that's 99% accurate at spotting tumors and completely ignores the blue markers. That's the goal. They measured this using something called squared distance correlation, a fancy way of checking how much the model's learned features overlap with the confounder. R-MDN's numbers were nearly zero, proving it's a game changer. So what's next? This isn't just about fixing biases, it's about building AI that evolves responsibly. From healthcare to autonomous systems, R-MDN shows us how to teach machines to learn fairly, adaptively, and ethically. The future isn't just smart, it's wise. Stay curious and keep exploring.